this is a talk that's tying together lots of different things I've been thinking about over the last, years really. So I named Definitely Destroying Deathstars because, link mate, right? But I wanted to answer a few sort of questions in this, like, what are Deathstars, what do they look like, are they a bad thing, what can we do about them if they are? Introduce some ideas of domain-driven design, because there's various approaches people take, and I think that a lot of the core ideas are kind of lost, right? Then I wanted to look at this from the perspective of looking at something enterprising and seeing how it scales. You can look at it in terms of, sorry, I'm trying to start watching. I'm talking way too long. Here we go, right. So looking at it in terms of a layered into your application, like everyone's been writing, various problems you hit as you scale this, and various solutions which you go through CQRS, event sourcing, and then introduce this idea of stateful services, which you met everywhere. And along the way, I want to get people asking some questions. So I'm going to tend to shoot down some things that I think are very commonly held, but are perhaps not quite true. So I'm John Nicholas. I like writing code, run a few companies, work for loads more, loads of different sectors, lots of different sizes. I've built 7 event source systems that make people money at the moment. Deployed several actor systems as well. I'm a contractor. And I do lots of coaching, training, well, not lots, but I do training, coaching workshops, and quite enjoy doing them. Kids, car, terrible sense of humour, and generally laugh at stuff going horribly wrong for all the right reasons. So, one thing that occurred to me while writing this is, if you ever have an original thought, and I just want to warn you that if there's anything I say that's original in this, it's probably wrong. Every good idea I've had has turned out to be spontaneous before me, and I like great fun reading about it. There's a big long list of names of people who I've read, talked to, and got ideas from. There are many, many more people who should be on there. Question everything is kind of what I'm trying to say. So if we're going to DDD, which is full of modelling, we should look at Conway's law, which essentially saying is every time you attempt to model something in an organisation, you're going to model communication structures. The inverse of that is if you're not modelling the communication structures, either you think the business should be run differently, change the business, or when you're modelling, right? It's a constraint, it's a load of options. So we're going to try and think about things more from a communication perspective inside of businesses. What is domain-driven design? It's a very difficult answer. The book is a very thick book. Eric Evans and Morgan, I can't remember his first name, wrote a very dense book. Many people disagree about the order in which it should be read. So I can't possibly script surface on DDD in the 25 minutes we're going to give it tonight. But they got these ideas from somewhere, and I think the language and the way they approach it came out of conversations they're having on forums in the middle of the 2000s. So if we could look at ideas from maybe where they started, maybe a lot of the ideas of DDD can drop out, and then we should be able to not only apply them, but also evolve how we're thinking about it. So I want to see if we can merge some of these ideas. That's the goal. So there's kind of 4 principles that I really like thinking about in development. As this talk is growing and the scope's increased, these 4 things have dropped into the background. But they're basically the idea of work done, physics equation. Work done is force times distance. An idea of craft, simplicity, and DDD, and mainly the act of refactoring within that. We'll get to that shortly, okay? But these ideas I'll come back to, and hopefully they'll kind of resonate throughout, okay? So economy of motion. Work done is force times distance. In this situation, distance is actually moving the business's capabilities. At one point you can do this, you want to move it so you also get something else. Distance is kind of a step function. You either achieve it or you don't. If you don't, the work you've done is wasted, right? It all kind of follows. The interesting part of this for me is the idea of force, in that you can make work easier or harder for yourselves. And maybe as we're doing this stuff, we need to be thinking, how easy is it? Is it as easy as we expect? How do we adapt this? The inverse of work done is actually efficiency. You can look at how much work you've actually delivered in this step over the total energy, work, resource, whatever you want to call it, the company's expended. And you get this colossal amount of wastage. So if we can start trimming these processes, the coordination costs and deployment side of the transportation side of it, you're going to get huge wins out of it. So it's coming back to this idea of simplicity again, right? You hold a weight, it hurts, right? So the second idea I want to talk about really briefly is craft, which I'm going to abuse the way it's used normally to mean that what I'm talking about is an awareness of how easy or hard something is relative to how you expect it to be. So when you're working with things and it's going well, everything feels easy, right? But when it starts backing up a bit, it's hard. So when you get into like repetitive tasks, for instance, you can start measuring these sorts of ideas. You realise that actually it takes slightly longer, or it takes the same amount of time every time, and that probably tells you that you're not getting better at stuff, and you can work with it. The way this means from a business perspective and architecturally is that if the business has a perception of a change being small, our goal is to have our bit of development work be small next to it. And when it isn't, that's our architecture failing, because that's the way our model is not necessarily aligning with how the business wants it to work. So I'm trying to get this idea of we need to be constantly changing what we're doing as new information is coming through. Another big idea of this is a guy called Rich Hickey did a talk actually for a Ruby on Rails conference about coupling and simplicity. One of the big things he's talking about that is the word to complect. It literally means to braid things together to make complex. And the reason why this is a problem is whenever you tie two things together, any future decisions have to take all those couplings into account. So I think at one point he even says that adding another stage of coupling in something actually doubles the complexity of the entire project. It's, you can quickly see it, because as the project goes on, you start finding things like you spend more and more time dealing with the past rather than adding value in the future. Another very big thing he's talking about is that good design is actually deconstructing and taking things apart rather than composing some horrible, complex beast, so again, I get inspiration from physics. You get these nice, tiny element equations, which when you actually apply them to reality, turn into 5 pages of engineering. But the idea is good. And so his big point is agility is simple, dominates all other forms of agility. And he's really passionate about it. The talk he wrote me. The last idea is TDD. But for me, this is really about starting at the end of what you're doing. It's about understanding where you're going, figuring out how the person wants to consume what you're producing, and understanding the value that's immediately there from that. If you don't understand that, you're probably not going in the right direction to begin with. We're not meant to be discovering stuff. We really want to understand where we're going. This TDD is red, green, refactor, right? One of the ideas I've only met in the last couple of years is kinesis. That's really, really powerful. It's a metric of coupling. It's describing how tied together bits of your system are, and also giving you an idea on how you can decouple those parts of the system. There's a talk given by, that website has a list of all the kinesises on them, from weakest to strongest down below. I don't have time to go into it, I really would like to, but it's one of the many things I'm just having to scratch the surface of. But it's a very powerful idea because it's about taking something that people do naturally and understand what they're doing, but providing a good objective language to then have this conversation in public with people. And that's, even if you disagree with the idea of kinesis, at least it gives you a conversation point to start from. Kevin Rufford, Jim Jeffries did a really good talk on this in Agile Manchester a couple of years ago. I would I'd probably watch that instead of listening to me right now. It's really, really good. And that's like the core principles of what I'm trying to get at, really. So you got, kinesis has 3 degrees, strength, degree, and locality. The idea is things that change together, should kind of live together. It's very sandy net in that sense. You can look at how many things you're coupled to and attempt to reduce that and pull it apart. And the really interesting thing for me is that the strength reconnaissance isn't about how bad the bug is, it's about how hard it is to detect it and how hard it is to fix it once you've identified it. Anyway, this is an amazing subject, and it's really, really good when you see someone who gets this, applying it, and working with it. So if you ever get a chance, I would encourage you to at least attempt to get into it. So anyway, that's a bit longer than intended. So the summary is, what I'm trying to get at is, we know where we're going because it limits the tree of possibility back down. It's like a design thinking idea. We want to decouple our systems because we know we want to change them. And we want to build systems which are designed to change, because new information is always going to come wrong, and it's going to always tell us that we were wrong. And because of this, our architecture needs to be all about decoupling and encapsulation to take those areas that are going to change and protect the rest of the system from them. But what about Deathstars? Well, kind of been talking about the inverse of them so far, but the mandatory Death Star, right? It's an interesting structure. It's about the size of a moon. It blows up moons. It's spherical. It has a central core. There must be these radial things sticking out of it. And if you think about this thing moving in space, if it moved, it would just have radial bits coming out of it. It's a inertial force that would tear it to pieces. It must have a hell of a lot of structural strength holding this thing together, like coupling across the system is what I'm trying to get at. And it's very interesting in that sense, right? Because we build systems which kind of look like this. We have lots of separate stacks, at least that's how we perceive them. They all go off in different directions. They all might have different owners. You may have different teams working on them. And you all think we're doing something good and separate until you start mapping how data and work actually flows through these systems. And then we discover that actually these different systems are very, very interleaved. This diagram actually came from, we sat down in a meeting one day discussing about a product. I've changed it all to protect the innocent, right? But we realized we were hitting 8 subsystems to achieve a simple task, and that's why we weren't able to deliver anything, because no one could know everything about every system. And so we kept having to talk to people, which is not a problem, but it's just a sign that it's working against your grain, right? So why am I saying this is a problem? Multiple systems are braided together. If you're going to get value out of something, you have to connect this to this, right? So that's not a bad thing in itself. But the real problem we're having is that we can't change these systems without getting in touch with the 1 or 2 gatekeepers in the business who've been there since day dot. And that's why we can't change, evolve, and keep moving at the pace the business wants us to. So I want to argue that we've modeled the problem wrong, slightly wrong anyway. And the funny thing is, I've never seen anyone do what I'm about to talk about on an enterprise scale, right? So I'm just trying to hope some people try it and don't destroy everything as a result, right? And I think a lot of places try and do this sort of stuff. But, so, how do we destroy Death Stars? Well, it turns out we don't. We just make smaller Death Stars, we make more of them. But, it's just where you get into this fun stuff. But I just want to ask a few questions at this point, right? Everyone's heard of the big ball of mud, right? Yeah, some nods. That's about 50-50. Right, so I probably should have asked who knows anything about DDD before we started, right? Because I'm kind of assuming a basic level. So a big ball of mud was in the page 1 of Eric Everton's treatise on DDD. He draws this huge class diagram of all these classes interleaved and overlapped on each other. And he's saying this is your typical system. It has no separation or segregation. Everything's just in this big, sticky, pyramid, monolith shape, right? And I keep hearing the word big ball of mud used in a negative way. It's an example of the system you shouldn't build. And, has anyone heard big ball of mud used in a positive way, right? No nods. Okay, good. Because the guy who wrote about the big ball of mud in his original article on it, it's a big long article, has a conclusion that says, it may well be that the economics of the software world are such that the market moves so fast that long-term architectural ambitions are foolhardy and expedient slash and burn disposable programming is in fact state-of-the-art strategy. And that kind of really surprised me, right? Because I only went and read that article because I realized Death Star sounded a bit like big balls of mud. And I should probably go and check that big balls of mud are in fact what I think they are, right? And then I discovered that actually they're not what I think they are. Big balls of mud are like a really valid pattern because they work and they're effective. So, you know, I learned something. I find that, like, you know, interesting. I want to keep pushing this idea of what you think you know and have known for like more than 10 years is probably not as true as you think it is. So anyway, where have we got to now? We kind of lean and mean. We've got this understanding that coupling's bad. We want to change stuff because we know we're going to get it wrong and we want to stay small and agile, right? So let's DDD everything, right? We got it. Stop. No, don't do that. And I apologize for my sense of humor at this point. It's going to get worse. So really, we want to ask when not to do DDD. Now I'm just going to steal off people, right? Greg Young argues that you can come up with a very simple heuristic for figuring out when and where to approach different ideas. His big one is ask for a given area of the business, what competitive advantage does it bring to business? Is it a part of the business that's going to make, you know, a large amount of money for them? Well, no, it's competitive advantage. It's not purely about revenue, right? It's about how is it going to separate them from the fold? What value does this add to their customers? And the other question he asks is how much work is it to build? He then builds a little 2x2 matrix. You know, if it's a small advantage and lots of work, you should buy it, right? If it's a large advantage and a large piece of work, then it's time to use analysis. It's time to model and go into DDD. But if it's small advantage and a small piece of work, he cracks a joke about putting crap developers on it, right? But I personally think that's the point where you go out and try something completely different just to see how it works, because you need safe spaces to work in, right? And my favorite one is large advantage, small piece of work, which I've put JFDI. I think you can figure out what that means. But mainly because, like, when you get into these like ideas about lean and stuff like this, really you should be taking those big ideas and big pieces of work and finding ways to chop them up into a couple of big smalls, right? And that's where you can really move fast and start unlocking stuff and leave that 20%, that's 80% of the work behind, right? So what should we do if we're going to do DDD? Warned you. Well, there's 3 ideas. Well, 2 ideas and a rant. The big idea is single responsibility principle. Has everyone heard of single responsibility principle? You know, it's kind of like a job interview question, right? Everyone should know this really well, right? So, don't drink and write presentations. So Wikipedia, if you look it up, goes, it's talking about a report. This is actually they've taken it from something Bob Martin was writing, right? And this is an example of it. And if you read Principles of Agile Development, he uses very close to this example. The idea is that there's a report, the content can change and the formatting can change. They can change for different reasons, so they have different responsibilities. So it would be bad design to couple these 2 things together that change for different reasons at different time, right? Everyone knows it's a trap. If you go and read Bob Martin, like the guy who coined it, wrote about it, and has spent years talking about it ever since, he approaches this from a completely different perspective. He's sat there talking about people all the time. The larger example also has a calculate pay function in there. So he says the calculate pay function is the accounts department, but this report is actually an operations problem. Therefore, you should be talking to the COO and he should have ownership of it. So you should separate these pieces of work by people, not by class name or function, right? So if you go and read that, you'll see that he says the word people, COO, CFO, CTO 25 times in 3 pages of text, right? You know, Greg Young has a great thing about trying to figure out who the owner of something is. You just turn it off. Whoever phones you up and shouts at you, your family stakeholder, you know. But it's that kind of an idea. Separate by people. So why did everyone lie to me, right? I've literally spent 10 years running around telling people something which actually is fundamentally wrong, right? And I find that really, really cool. Because I think everyone else has as well. You know, this is about, there's a full story and there's a bit of a story, and everyone's read the first example but not understood the second example in the book, right? So what about the papery quotes, right? Well, that was really dry. It was written in 1971. It's massively academic, and the gist of it is basically encapsulate difficult design decisions because it's really hard not to. But it was also comparing it to a flowcharty approach to development. and saying that if you scale a flowchart past 10K lines, it's going to start going wrong. So I want to paraphrase Bob by saying, encapsulate decisions made by important people because they will change their minds in a way that is guaranteed to break your code no matter how you factor it. Because I think secretly they look at the source code and actually just want to mess your life up. So, you know, this is about getting back to this idea of refactoring is perhaps not a pursuit of an aesthetic idea of beauty. There is actually a function you are performing of decoupling in there. So that's kind of that, right? So single responsibility is all about people separating systems by their owners, which often may mean duplication of little bits of data or behavior, perhaps, right? And the reason why we want to do this is because different owners will pull the system in different directions. And so because we want to stay proportional to the business's perception of the size of the change, maybe we want to actually take that into account fundamentally in our architecture. As in, our job is to model the business. It's not to model whatever's simplest for us to write. Intriguing, I hope, right? How many other areas of common knowledge are like this, right? You know, for instance, let's look at this solution. If anyone can tell me what the solution on the left does, I'll buy them a beer. You know, the one on the right, hopefully it's pretty obvious by the time you've read it now, right? Point being made, behavior is way more important than classification. That might be a bit out left field, but the point is, it is about responsibility, understanding why rather than the what. So boundary contexts. Well, we've already actually talked about boundary contexts, I think. But if anyone here actually knows anything about DDD, I might have to justify that to them a bit. So a boundary context is an ubiquitous language. Has anyone heard of ubiquitous language before? Anyone not heard of it? No movement? Okay, a couple of hands. So an ubiquitous language is when you see I'm speaking up to speak to the back and have a mic on. How messed up is that? So an ubiquitous language is an agreed, common, shared language, which when you discover you need to change it is an interesting situation. So when you're talking to people, you discover groups of people use the same language together, and that's the basis upon which you start modeling your system. The reason why it's a very powerful tool is that the more people you talk to, the more chance you have of discovering that different people use the same words to mean very different things and have very different behaviors attached to those words. When you discover that's happened, you've discovered what a bounded context is. It's the boundary of the context of that language making sense, right? Some examples of this are, wow, I'm actually speaking slower than I meant to. So some examples of this are the word customer is really overloaded, orders overloaded. The classical DDD example is the policy, but I don't know insurance, so I'm not going to talk about it. So a marketing department, when they talk about a customer, this is someone who hasn't necessarily interacted with the system particularly yet. It's just details they've got from somewhere. They've not placed an order. There's no money attached to it. The accounts department may not have an idea of a customer either, but they will know it's someone who effectively is the revenue stream, right? A warehouse, funnily enough, a customer is just a label, you know. They're completely different. And this then leads you to the other core idea of DDD, which is aggregate roots. But the thing I wanted to bring out most of all is that boundary context and single responsibility principle, when you separate them and start thinking about it in terms of people, actually become very, very similar concepts. I reckon boundary context is really a specialized form of single responsibility principle. So if you can get your head around that, you can probably derive a chunk of where I'm going, right? So we can separate our services based on this stuff. And that's what I mean by an aggregate root. It's an entry point into a bounded context. And different areas of the business want a different entry point. We've already talked about the purchase journey. Obviously a customer on Amazon, the customer's interacting with the site. All the functions on the domain will be against the customer, right? The warehouse, they're probably dealing with orders or order line items. And so their idea of an order is actually a shelf location. It has nothing to do with whether it's a blue size, blah thing. Well, it might do because they might be on different shelf locations, but you know, it's definitely not about the basket, the promotions, the, you know, all that stuff, right? So what I'm trying to say is if we decouple these different areas and we keep them very separate, and we don't try and solve the whole problem in one place, instead break it into many problems, each bit becomes orders of magnitude simpler to deal with and reason about and develop. And that's really what I'm trying to push at. ORMs. I'm not going to do it. ORMs and DI containers are the things I love ranting about most. I hate them. They're absolutely brilliant for like 90% of your development problems, right? They fix exactly the problem you want. They provide you a nice, easy way to go forwards. But I'm interested in like the fun, difficult problems, right? So what I'm going to do, very short on time here, I want to look at some code. I want to go from a n-tier service and then look at different ways we can nudge this, right? And also think about what we're getting out of it at each level, right? So it's called an anemic service, right? But it's really not meant to be, oh, here we go, never do anything live. That's what I'm learning here. Go away, yeah. Right, so it's called anemic, mainly because it's a very thin domain. It's not a derogatory term. It's to say like 90% of the stuff you do, if you're not wanting to actually model a domain in detail, it's just like pretty much perfect, right? So it's a class, it has a constructor, it takes some repositories, it's nothing magical. And then there's this function in here, right? The function's called create order. It takes some basic stuff to do with an order, customer ID, a basket ID, presumably it's going to look up a basket, right? We're going to do some validation on it. And then what we're going to do is we're going to go into a customer repository and pull a customer out. We're going to go into basket, we're going to pull the basket out, right? And we're going to use some magic values to determine whether those things have been successful or not. We're going to use null in this case. Could use -1 on the ID, right? It's a common thing if it doesn't exist. Or it'd be 0, wouldn't it? -1 would be a new one, right? But magic numbers. And these are all ideas of, you know, in essence, you're coupled to things, right? So we're going to get a customer, we're going to get a basket, and then what we're going to do is we're going to go to the order repository, say, make me a new order. Then we're going to mutate the state of the order. Then we're going to tell the order repository to save. Now, that is great, right? There's nothing wrong with that. The problem is when you start getting onto more complicated ideas, all your behavior is going to be in one place, right? It's not going to, when you start going into object-oriented stuff, you actually want to push the behavior into the objects and into the domains, and that way you can start building up way more complex behaviors based around a much more, you know, I'm trying to think of the word, intuitive? It's not really intuitive, but much more like expressive language-based approach to it. So we've got this create order service. There's nothing wrong with that. But under it, we have another function, get customers order history. We've got another one, get today's shipped orders, because it's all to do with orders, right? And there's one underneath this, which is update order status, because that's going to be used all over the place, right? And that's like your standard n-tier thing, right? But there's various things we can do, right? I've broken all the code, that's the way it works. So you get into this idea of CQRS, which really is a way of taking your code and just separating it out, making it logically a bit more organized, right? The idea is you separate your commands and your queries. So the central idea is that your things which mutate state return nothing, and things which return data don't mutate state. So we're going to pull them out and put them on one data store. I don't think this offers much advantage, right? You can start splitting your databases out. You can have a leader database that you do your writes to and replicate it out that way. But it's really a logical win you get in your code bases from doing this. What you find in most companies is the query side of it's hammering. All your load is on the queries. And you're querying a third normal form database, and that's not necessarily the most efficient way, which is why NoSQL's taking off, right? So let's look at, before we get on to like how to adapt that, let's look on how you might change that piece of code to make it look a bit more like this, right? So I'm gonna jump around a bit, right? And try not to swear at computers. So the first step we might do is take that order service and break it into two separate contexts. We've got the customer experience idea, and we've got an operations idea below, right? We've got the same functions. We've still got create order, order picked, order shipped. Well, it was update status before, but I've split that out to something a bit more meaningful, right? So now we're saying the order shipped rather than update order status to shipped, right? But the idea, real idea here is we now on create order, we're not returning anything anymore. When we want to create an order, what we're doing is we're getting a customer back from somewhere, we're calling create order on that customer, and we start passing the dependencies in it. We've like completely reversed the direction of where the dependencies are. Before everything gets pulled out and it's like inside out and the top level of the service, we're trying to tuck it all back in and build some kind of like graph structure off it and attach behavior to the various parts of it. So this works quite well, right? I'm not going to get into the customer at this point, right? So we then split the operations side out. We do the same thing with order picked. You know, we do the same thing with order shipped. The thing is, this all looks like it compiles, but we've got lots of arguments floating around, and it turns out that this function's actually backwards, failure reason and shipping number are the wrong way around, but because we're just using strings with an essence of meaning in there, we're not picking it up. We can factor this out into types and it'll all compile and tell us when we're messing it up, right? So we can do a couple more things to this, right? We can start factoring out these functions into proper command handlers. And trying to see if I've got the right piece of code, you end up with something that looks much more like this. You end up with your application services with your receive handlers on it, taking a command. You then start mapping the primitive types from the command handlers onto, use money, onto your actual domain object, the customer, and you push it through. And you've got to CQRS at that point, right? On the read side, you just plug it into Entity Framework and it looks the same way, right? Because it's on the top of your database. That's a very simple example. I'm overrunning. So CQRS is great. The problem is the load's on the query side. So what you do then is you split your database in two. You have a read model, which you key value pair, something like that, and a write database. Both sides of this thing though, so the thing you get from doing that is you have two different forms of, cat theorem, right? One side is available and the other side is consistent. Your right side, you want to be massively consistent. Your other side, you just want to be really quick. So you pull these two bits apart, you can now scale them independently and you get your performance goals out of it, right? The problem you run into though is you now have two records of state in the system. And you're going to make bugs, things are going to go wrong, the system's going to grow, and at some point you're going to realize your state's inconsistent and you have a very, very hard time unpicking it. So you can move to something where rather than recording the state, you start recording the reasons for change, the context of what's happening, the user's intent, right? So you can start recording the events off the back of the user's intent. So now when you receive a command, you can put it into your aggregate route again, you reload your aggregate from your events, you can affect some external systems, and if all those things are successful, you can write your event back to say, win. At this point, you can start using subscriptions to generate your read models, your key value pair read model, or however you want to do it, and then have a really thin domain on top of it. And then when something goes wrong in your data stores, you now have this list of what the user was actually doing, and you can replay it back through it and rebuild it when you patch up your system. So you end up in a much safer place. Oh dear. So I quickly knocked up an example of this. I might cut this short and just leave a link to a repo for anyone who really cares. So I knocked up an aggregate for a customer just to sort of try and get at some of the ideas. What's going to be the easiest way of doing this? So I have three tests. I've got register customer account, right? It just calls and passes a register customer account command in. There's another one for add payment type. So it registers an account and adds a payment type. And there's another one for register an account, and then we're going to add an item to a basket, right? The fun part of this isn't the tests, it's how the customer reloads itself. So the customer has a, fortunately I've got a real thing for Lambda at the moment, which might make life a bit difficult for people. So, I've got a function here called build load customer, right? It returns a function that will load the customer for given an account name. But the other dependencies that are needed to set your customer up properly are passed in as arguments to it. So, for instance, we need a payment provider, we need an event source for the data. And so that's all then passed into, we use closures to get that. So when we delegate to the load function, all we do is we pass the account name into the event source, then we take a new empty customer in effect, and we do a left fold across it and apply the events we get back out of the event source onto it. Well, so let's look at these simple application things. So when you apply a register customer, all you do is return a new customer with the data from the event in it, right? When you apply an add item to basket, well, you take the customer you already have, and you add an item to its basket, which will give you a new basket because everything's nice and immutable. Then you create a new customer and pass that new basket into it, and you've now applied two events to it. If you go a bit further, and you add a payment method, where you take the customer again, you extract the payment method from the payment method factory, and you return a new customer with it in. And so you're constantly able to roll forward with any sequence of events by gradually updating the state of this thing. And that's the load side of it. And that's the complicated side of it, right? The other part of this is when you actually come to add an item to a basket, right? So on a test, say, in one of the tests, just to kind of, if you add a command to the customer, for instance, add new payment type command through a service, it literally just loads a customer up from the function we've just seen, and then it calls on that customer add new payment method. And all add new payment method has to do, it doesn't need to mutate the state of customer or do anything to the customer. All it needs to do is decide, has this operation succeeded? Have I managed to affect the external systems in the way I expect? If I have, then I can write an event saying that transaction was completed. So you end up with this phenomenally decoupled, simple way of, well, the loading way you might not think simple, but it is when you get into the rhythm of it. But the application way of it, of this data, is it's crazy. You can, by taking this kind of an approach, you can completely decouple your design of the UI from understanding how you're going to do any of the work. You can build these things entirely separately because you don't need to know how to consume the event. You just need to know that the event exists and you've written it and what stream you're going to put it in. However, I'm 10 minutes over. However, I'll just close Rider. Event sourcing comes with a really big problem. You can scale the query side. You can do this aggregate stuff. A user interacts with a system. You can spin up your aggregate. You can load stuff. You can go off. You can write your event. It's all consistent. It feels good. Up until the point that you need to update something from two different places, like a ledger is a good example. Like kids arguing over a packet of sweets, right? They're both fighting over the same resource. If you load that aggregate up in two different places and make a decision, you're going to end up with a consistency problem. You're then going to write it back to your event store. When you rehydrate your aggregate, at some point, you're going to break some rule. So event sourcing like this, and it is a bit of a straw man, works really well, provided you know you're only ever going to spin up one instance of an aggregate at once. We can get around these other problems, but they involve actor systems. I just realised I've not put that back on present. Yeah, so you get to actor systems after this, and stateful services, and that's probably the point we should have a break. So that first half went on actually a lot longer than I planned, which really sort of blew my brain a bit because I was expecting to get it done in about half the time that I practiced it in, right? So I didn't do any sort of summary or quick explanation of event sourcing and why it offers some advantages that maybe, sorry guys, so it offers some advantages that other approaches may not offer. It also offers a lot more hard problems. I think it has more simple components to it, but they add up to a hard problem that's, I don't want to say complex, I don't think it is complexity. I think it's just generally difficult problems of computation. When you distribute things over a network, you get indeterminacy coming through and things get very difficult to deal with. So a quick summary of like what's happened, right? So there's some rules of event sourcing, right? The right side should never read the read model. You want to keep them separate. Otherwise, you have the consistent side trying to read potentially inconsistent data, and it will blow up in your face. Hard experience. I've drawn this diagram here. This is not your whole system. This is just one circle of an aggregate root, right? This is one bounded context, perhaps, right? There are many of these sat on top of each other. You have many subsystems which look like this. That's kind of the fun of it. You can keep them all separate and scale them separately. When you process a command, an event essentially is committing a transaction, and reloading events into an aggregate should not have any side effects. If they do, you're in trouble. Because, for instance, you'll start spamming people with emails every time you load a customer up, or you'll start subtracting money from a bank account, right? It's never going to be good. You get this idea of a projection, which you use for read models. Like you might sign up to certain kinds of events, such as item added to basket, money debited, anything really. They're like types of event. You can sign up to, say, streams. Greg Young has a cool piece of software called Event Store, which provides 3 good projections out of the box. One is you can reload an aggregate stream. You can get event types. You can get categories of events, such as if you have a stream called customer-ID, you can reload all events to do with customers. And you can start doing some very cool projections, read model-wise. Notifications, something else you can do off this. It's just a different kind of projection. And it turns out that actually your aggregate, which you're reloading in your domain model to then do something with, is just another projection. So, it's projections all the way down. You get some really cool bonuses with event sourcing. Like it gets very easy to start plugging stuff into like Neo4j, edge databases, and building up relations and ideas of, you can start doing ML and stuff, AI, it's lots of cool stuff. Event storming is insanely powerful. It's very simple to do. It basically involves mapping temporally all the events in a system. You can get lots of different stakeholders in a company together, perform it. Google it, it's really cool. I don't have time to go into all the analytics side of domain-driven development, right? So the summary of what we've got is we're going to break systems down according to the people who own them. That's going to give us bounded context. We're going to model by behavior. And now we can start changing all this stuff faster independently of the other bits of the systems. We don't understand, but we've been told by some crazy guy with a beard that one side of the system's consistent, the other side has high availability. You can sort of trust me on this for now. I'm going to go into this a lot more coming up, right? And you have an understanding that event sourcing involves reloading an aggregate every time you have a command to get to its current consistent state. And if that seems like a lot of work to you, then maybe actor systems have something for you. The reason why you're doing that, though, is you're getting to the guaranteed latest known source of truth about an aggregate, and that's very important for consistency. So actor systems, because concurrency is like insanely difficult, and actor systems allow you to start having stateful web services. And I've never done this before until I started playing with Phoenix, and then realized that you can do the same thing in Echo.net, and what you're building is actually technologically something very, very different, and that's kind of cool. An eventual consistency joke. If you don't get it now, you will do later. Actor axioms. So we have this idea of actors. You can send messages to them. You can receive messages. They can only do 3 things when they receive a message. They can create more actors. These actors all have an address. In Akka, I'm pointing at a screen. You guys can't. Weird echoes. They have an address based on the system root in the user space. Actor 1 is the name of an actor. I know from looking at that actor is span up a child, and that child is also span up a child at some point. That's why it's A1, A1. The next one might be called A2, imaginative, right? Actors can also send messages
to other actors by using their address, and this is how you get location transparency. It's like a phone number. You don't need to know where somebody is, you just need to know their address and you can talk to them. The other really interesting part of this is an actor can say what it's going to do with the next message it receives. In an object-oriented language, this turns into a state machine kind of problem. You can decide what messages you're going to handle next. But in a functional language, because you've got no state in an object, a lot of the time you're passing state in as an argument, and you're returning tuples with like a success status and a state object. Well, that state object often also contains information about how you're then going to act in the future. But basically, you can create actors, you can send messages, and you can decide how you're going to handle future messages. And you're going to pass your state on to the next call, which in an OO language is mutating your private state. An actor is actually a fundamental unit of computation. If you're writing C# all the time, you're actually kind of writing an actor model, but you only have one actor, right? A fundamental unit of computation has three components. Processing, the ability to sequentially process code. Storage, actors have private state, and they can communicate. They can send messages via addresses to other actors. And they're isolated, they live on their own, which is the reference to Leibniz and monads. It's not a functional monad, it is the other kind of monad, right? No, I just got to that. Actors have no windows. Leibniz monadology, monads have no windows. It's always made me think, the hell was he talking about? Then I started using actor systems and it's like, that's cool. They're like a little private bit of consciousness, right? They have only private state, you cannot modify it externally. And because of this, in OO languages, you have to be a bit more careful because everything's passed by reference. So you should really be using immutable types, which is why in that customer event-sourced aggregate example I gave, I was constantly spinning up new customers and using immutable lists to, instead of adding an item to an existing basket, we returned a new basket with the item added to it. And then constructed a new customer, passing that basket into that customer. And garbage collection works to your favor in this, funnily enough. Akka.net, well, actor systems are all about concurrency. Concurrency is like a first order thing. The abstraction is built for that first. You get a lot of other good stuff, but I'm really wanting to focus on the fact that you can take some very, very difficult concurrent problems and model them in a way that is, trivial. And I'll hopefully show or talk to you some more if we've got time later on. So, traditional ways of handling concurrency are things like continuations, they sync await, tasks. They're all a form of single-threaded ideas based on lambda calculus, right? And these languages are very, very good at doing that kind of shopping list processing, right? But every other time you hit concurrency in these, they're trying to pretend it's not concurrent. And so you end up with these like shared state, resource contentions where you get mutexes, semaphores. All these things are trying to pretend that you're going to get deterministic output based on a function. But you're not a lot of the time, right? Because we're talking about slightly bigger systems now. When you look at the Intel processor bug, right? It's a great example of the fact that we don't want deterministic systems anymore now. We want to use clever prediction to do things. Sorry, digression, that's why it takes too long. Turing machines assume deterministic output. I can't remember where I've taken this from. It's from people far greater than myself. But the idea is that Turing machines are basically cogs, whereas the machines we're dealing with have, there are basic network partitions. There is time in between the sending and the receipt of messages. And when you have multiple things sending messages to the same place, you don't have guarantees on the timing it takes for those things to get sent to a place or on the amount of time it takes to process. Everyone must have worked with a message system where an exception gets thrown somewhere, but because it's parallel and the exception takes so long, everything gets out of sequence. It's very difficult to handle in a normal concurrency world. But in actors, we've built them so that these problems are features, right? Spot the developer, right? It's not a bug, it's a feature. So active communication. So actors don't talk directly to each other. You may think you are talking to another actor. You have an actor reference and you send a message to it. You're not sending a message to the actor reference. The actual actor you're sending a message to is buried inside other actors, right? And this composition has a mailbox, it's a message queue, a FIFO queue. It has an actor, has other things. There is the supervision hierarchy gets involved in this. You've got the supervisor looking after it. It's all kind of tied together. Not so important for this. The point I'm trying to make here is when you send a message to an actor, you're basically popping a message onto a queue. And each actor just processes one message at a time in a very synchronous way. The thing we run into straight away is what happens then when I want to perform something and want to do something later on. You know, go and do something and afterwards do something else. You usually fire up a task you continue with. That's kind of a form of a future, but that's attempting to model it in a synchronous fashion, right? This future is very different. A future in an actor system is literally you create a new actor. That actor has some behavior in terms of what message it can do. You pass the address of that actor to whatever actor is about to do the piece of work. When that actor has done the piece of work, it sends a message saying, I've finished, to this new actor you've created. That new actor could do anything at this point. It could simply notify you. You may have many actors, which you've all started working, notifying back to this one guy, who's then going, okay, I've aggregated the results of this. You might use this for logging. You can compose actors like this to start thinking about things in terms of attributes. You know, when you've got your next handler and stuff like this, you can start chaining these things together with concepts of like routing and things like that. Futures are an incredibly powerful, flexible, open idea in that respect. You know, like everything's an actor, technically everything's a future, right? So you get no more deadlocks, everything is distributed, and you get us, which if you work at dunnhumby might make you smile, but you know, that's what you get. So, does everyone know the TCP/IP joke? No? Oh, it's a piece of legend. I assumed everyone would know that one, right? So I'll have to read it out, right? Hi, do you want to hear a joke about TCP/IP? Yes, I'd like to hear a joke about TCP/IP. Are you ready to hear the joke about TCP/IP? I am ready to hear the joke about TCP/IP. Here is a joke about TCP/IP. Did you receive the joke about TCP/IP? I've received the joke about TCP/IP. Excellent. You have received the joke about TCP/IP. Goodbye. And that's literally how the TCP/IP protocol kind of behaves. Well, it's not literally, obviously it's a joke, but figuratively? I don't know, I never get that right. But that's a TCP/IP joke, and I love the bit at the beginning, which is why I actually saved this Twitter message as soon as I got it, because the image is a TCP/IP joke, the tweet's a UDP joke, I don't care if you get it. And now, you know, it just tickled me, right? That's what you get with actor systems, right? You get the ability to have, at one end of the scale, complete consistency, and at the other end of the scale, complete availability. And it's up to you to figure out and draw the sequence diagram and fill in the pieces about, you know, how do you want this protocol to behave? That might sound like a bit of work to begin with, until you realize the trade-off is you no longer have to think about concurrency. You're solving concurrency from the very beginning of this problem. So all these horrible race conditions and stuff start falling away because you realize, hang on a minute, I need something to negotiate a transaction effectively between this guy, and I want to deal with the result. Well, I'm going to spin up a transaction negotiator actor, which has some behavior in it. The people you're talking to will have some behavior in them. There'll be a little state machine. I'll get into this a bit more, but you can draw this stuff very easily in terms of flowcharts and sequence diagrams, and then you can encode it into actors very, very easily. And that's where the power is. So UDP is at most once delivery. Actor systems don't actually have UDP, it's quite funny. The ideal actor system makes no statement about the transport channel or protocol used, because if you imagine local code, it's just a function call. It may go through a few things, it might internally, maybe all kinds of thread magic happening, right? But there's nothing involved there. When you then scale up and go over a network boundary, it's the same thing. There isn't necessarily any particular protocol. It's up to you to make that decision. So at most once delivery. guaranteed delivery is a fallacy. We have very complicated systems built to solve this, TCP/IP being one of them. That doesn't even get into message sequencing and ordering. But if you do want guaranteed delivery on something, you cannot guarantee the length of time it will take to get that delivery, right? And this is where indeterminism comes in. So let's say you want to take a system that is at most once delivery and turn it into something that has a guarantee on delivery. On one side over here, you'd have an actor that sends a message over to the other side, and you'd have to create some kind of event ID. And then you'd introduce an idea of persistence. You'd start storing that event ID, and you'd say, you know what, if I haven't heard back in 5 seconds' time, I'm going to send the message again. And this guy's just going to keep doing that until he hears the message back. The actor over here, when he receives a message, the first thing he's going to do is go, oh, there's an ID in that, I'm going to send that back to sender. And now all of a sudden you have guaranteed delivery. The downside is, now this guy over here is going to potentially receive multiple messages. But that's a trade-off of the system. You can deal with that, by the way. You just introduce state on this side with a bit of persistence, and you say, you know what, when I've seen this message ID over here once, I'm going to pass it on to whoever wants to consume it, and then next time I see it, I'm just going to ignore it. I don't care anymore. And now you've got like guaranteed at-once delivery. But the costs and the protocol can be modeled and written. The good news is many people have solved this problem, and you can just download off-the-shelf things. But you can write it yourself with 20 minutes of effort, right? Because you can draw the sequence diagram. It's actually really simple. And that's what really got me going with Akka, right? So we started with event sourcing, and we're saying that concurrency in an aggregate is quite difficult if you have multiple things contending for the same aggregate at the same time, because you may reload that aggregate and an external operation may take a period of time. You may be hitting a database, you might have to hit some government service somewhere, in which case may never see you again, right? But you're going to run into overlaps of commands overlapping on the same aggregate. And this is not a problem while you only have one of them. But if you want to spin up and have a situation where you have high availability, but also good consistency guarantees, you start having to think about it a little bit more. So how do we get back to this, right? Let's find out state machines. I'm a big Erlang Elixir fanboy. They've got OTP. It was the original actor system effectively was written in Ericsson language or Erlang. They've solved lots of this stuff, right? But their state machines work very differently to Akka.net. And I actually really like the way Akka.net works. It feels neater. So here's an extract actually from one of the Akka training boot camps. I have a lot of code here, which I'm not actually showing you, because I did a load of prep and I've decided the code's just going to blow people away and glaze them. But I've got a repo, so if someone can remind me at the end, I'll share the repo with people. This is just a bit of one of their examples of the big problem. The bigger piece of software is attempting to go to GitHub and start scraping repos for users and then repositories for those users. So it's like a big fan-out operation, and it demonstrates scaling on this, right? This is just a little part of authenticating against GitHub. And I like it because it's a very small, simple state machine, right? Dear, throat's going. So the key in this is the authentication actor, third from the left. When this guy is created, she, whatever, right, becomes authenticated. It becomes unauthenticated. At that point, it can only receive messages that are to do with that handler. I'm going to show you the code for this in a second, right? You then receive some input. A lot of these systems, I keep coming back to physics because a lot of this stuff for me feels like impulse. Something hits the system and you just see it just scatter across it. But maybe that's me spending way too long thinking about this stuff. So you get some impulse coming in, an input. The actor starts handling it. It changes its state to become authenticating because it's doing some work. At this point, it can no longer handle input messages anymore because the only messages it can handle are the ones set up in that receive handler. It then goes away and it attempts to join a channel, and depending on the success or result of that, it sends a message back to itself, and that changes its state. In this case, the message is failed, so it becomes unauthenticated, which takes you back up to the to this point where it was last unauthenticated. So now it can start receiving input again. So that's like a mini state machine without too much code, right? Because I want to talk about what you can do in state machines. You can become something else. You can set up a new set of handlers. You can unbecome. You can treat a set of becomes as being a stack, because sometimes you'll have multiple ways of ending up in one state, and often you'll just want to bubble back to where you were before, right? So unbecome's a way of popping off the stack and becoming that. Incidentally, pop's a command that really knackers you up in CQRS, right? Because it has a side effect and you get something back. So these things don't always work very well, right? Like there are exceptions to every kind of rule, right? Sorry, it's a complete tangent there. Ooh, sorry. So you can become, you can unbecome. When you're now unable to handle a message or any message, you can optionally stash that message, which means you basically store it somewhere. It's like, in fact, all this event sourcing stuff, you can literally think, Git, you know event sourcing, right? You can just go and stash it somewhere, and then later on you can decide to unstash these messages, which will just pop them back onto the mailbox, or push them back onto the mailbox, and your actor will start cycling through them again. So it enables you to, say you've got something that wants to start work, but internally it needs to, do some other little process. Then when that finishes, you can queue up all the other messages saying, please do this, please do this. When that's finished, you can then add them all back onto the mailbox, and it will take the next one off and get on with doing it. It's also interestingly, before we're talking about aggregates, when you're reloading an aggregate, sometimes events can get written out of order. Well, it turns out if you have a state machine for something that's reloading, you can determine what messages you handle at that point. You can stash the ones you can't handle at the moment, and then when you unstash everything back onto the mailbox, you get this like cheap sorting mechanism to get behavior in an order that might make sense, right? You can abuse this stuff in really cool ways. So now we have state machines, we can build protocols, right? And a protocol is roughly described as multiple actors moving through a set of states in a way that's sort of coupled together over a large distance. And you can do this in order to verify a transaction. So what I'm trying to say is if you can do like CRC cards, and you can move CRC cards around on a table to agree how something should get done, you've just built a protocol, and you can do anything in the world. Wow. Buggily, right? So I've stolen a slide off a guy called Aaron Stannard, one of the people who founded Echo.net, because he was talking about cap theory and protocols, and he had a really good example of a distributed transaction, which is the question you get asked most in event store systems is, if I have something coming into a system and it involves multiple external dependencies, and one of those dependencies fails, how the hell do I get out of the mess I've just created? And the answer is, don't know, talk me through it, right? You have to work in a particular way. So I'll get back to that in a second. What I really want to point out is this bottom example here is actually the exact thing we came up with when we're talking about writing an event to event store and then projecting it into a read model, right? A command comes in, writes, some operation happens, which then causes it to commit an event. There's something effectively subscribed to that, there's a notify happens, so it gets pushed to it, gets published somewhere, something gets there, and then it then writes that event to update some state or do something with it. That is a read model, right? Which is kind of cool. This top one is kind of a monster, right? But it's very important because what happens is when you scale something on the command side out across multiple nodes, you run into a horrible problem when two things in different availability regions ask for the same resource and try and execute a command on it. Everything happens at the same time, and things, you can't guarantee the order of it, you can't guarantee the right one will get rejected. In fact, there's no way of defining what the right one is because you're in this weird world where there's no shared concept of time between these two things, right? It's just stuff happening. All you're seeing is information moving around. So you build a protocol to deal with this. A command comes in, the first guy gets it and he goes, okay, I'm going to start a transaction. This transaction involves multiple other parties. So I'm going to say to you guys, can you accept this transaction? Each party receives it and it goes, okay. I'm now going to go into a state that says I am currently processing a transaction. You then ask the system on their little world of consistency, can I process this transaction? Oh, yes, I can. I'm now going to reserve whatever's required to do that. These different things will then message back and talk to some kind of future and say, I'm okay, I'm okay. When one of them blow up, the future can then talk back to the original actor and go, nope, don't do it. At which point it goes, cancel the transaction, everyone gets notified it's cancelled, and you all have no effect left on your systems. If it was something that worked, obviously they'd all write back and go, it's all gravy. The first guy would then talk to the other systems and say, okay, please commit your transactions, go back to a state where you can process more commands, and now then the first guy would then commit his transaction, and everything would just flow, right? That sounds like a lot of words, right? It sounds very complicated. But you've just solved one of the hardest problems you're ever going to meet, you know, and it's literally just that diagram there, right? And that made me really happy, you know. Yeah, and that's kind of the point of actor systems, I guess, is it allows you to take big distributed problems and turn them into really simple diagrams and write code that you're almost guaranteed will work. The problem is, with concurrency, is there'll always be problems you never expected because concurrency is hard. How much time is that? 26 minutes. Does anyone not want to look at any code? Have I destroyed everyone yet? Oh, apathy is strong. All right. So here is some code to create an actor system. The first 2 lines, well, you only need the second line actually. So boom, actor system.create, you give it a name, you pass in a config file. This config file is actually empty, but it still works because you don't need config to set up an actor system. I've then got the action that'll land there is just to write to a console out, and I can pass that through the actor system and then map it out right out to the console, right? The line after this is that's actually creating a brand new actor locally. System.actor_of creates the actor, and it's creating an actor with props. You can actually create an actor far simpler than that. I need a bit of DI there, so I'm going to use the props. You can literally just go system.actor_of, boom, in angle brackets, the type of the actor, open, close. If it needs no constructor arguments, that'll give you an actor. This is, if you've used React, you've met props. It's just a way of creating a factory function to create an instance of it later on when you need it, right? And then lower down, that's systemActor.tell. You're telling an actor something, and you're just spinning up a new instance of an object and passing in the information. In this case, it's the input. So before, on the authentication example, which you guys will have completely forgotten about, there was a service actor, and that's what you're talking to here. That service actor forwards onto the authentication actor, which is what we were talking about. This one is the authentication actor, and what I'm going to show you here is a bit about the state machine. What we have is the constructor at the top. It's just setting up the actor. In fact, all right, you can't see it. Sorry, I thought I might be able to connect those 2 constructors together, but it does it inside itself. So the first thing this actor does is it becomes unauthenticated. Now, unauthenticated is just a function, but in that function it sets up some handlers with some messages. It can receive an input message and it can receive an authenticate message. The actor, when it receives an input message, all it does is it tells itself to authenticate, right? So you're translating from the external world into your domain is kind of how I'm seeing this, right? So it tells itself to authenticate. Then it goes off to GitHub, sets up some credentials. It changes its state to become authenticating, which I'll show you in a second. And then based on the results of this .current, which gets the details, it does a continuation and it returns one of 3 different types of object. And oh my. It turns one of 3 different types of object. Never move the mouse, right? And then it pipes that back to itself. That pipe2 command is an example of a future. What it does effectively is it spins up, about to say something that's technically not true actually. It sends the message back to itself, right? So you have, so because the continuation is of type object, you can return one of 3 different types of object and it just sends that thing back to itself. So once the task is finished, it keeps the reference to the current actor, the self, and then pipes the message to that reference. So it then receives those messages, right? And those messages are here. So what we saw in here was become authenticating. Wrong way, sorry. What we see in there is it becomes authenticating, which calls the function become authenticating, which says become authenticating. I hate this pattern, but it's the way a lot of people do it. And in authenticating, it can handle those three messages. Failed, cancel, success, right? Which, you know, you can either be failed, cancel, or success, right? So you can't receive those three messages while you're in the very initial state, and you can't receive input while you're in any of these other states. So no matter how many things are trying to tell this thing to do something, it's closed off its behavior. And that's very, very powerful. What I've run into recently was Rabbit, consuming messages off Rabbit. If you subscribe to a Rabbit queue, you're going to spin up multiple threads, right? And your handlers are going to all be on separate threads, and you're going to have separate messages being processed through your system. What I had was like a fail-safe switch on the system, which when something blew up, I wanted it to reset and go into a state where it would check its external dependencies were safe before I started consuming messages again. Unfortunately for me, the first version of this didn't think about Rabbit being multi-threaded in the way it is. So I then started off 8 fail-safes of this thing, and when it passed, 8 of them resubscribed to Rabbit. So now I have 8 consumers consuming things, and when they blow up again, it repeated, and now I have 64 consumers consuming things, and it blew up, and I went for lunch, came back, and I had 2.5 subscribers to a Rabbit queue. Not great. So introduced Akka.net, introduced this very same pattern here in effect, which is while I'm doing something, don't process start messages. Now I've finished doing work, I can process the start message again. And like that, there's no concurrency problem. I don't need to think about sync locks, mutexes, semaphores, anything. It's just done. There's no thread pools, you know. And that was really, really cool. I really like that. And that is kind of that. Cool. Well, thanks very much for not running away halfway through.
Thanks, John.